Here's a review problem on fluid statics from the AP Level B exam from the year 2012. This is problem number 3, and this problem has to do with the equation that says gauge pressure is a function of depth for fluids at rest. Gauge pressure is equal to density times gravity times height, and so we're shown a tube that's filled with 3 liquids: oil, mercury, and water. And this is when the tube reaches a case of static equilibrium. You can see the oil sits a little bit higher than the water. So the oil must be less dense than the water. The pressure at point A and the pressure at point B have to be the same. If there was any difference in pressure across the ends of the mercury, then it wouldn't be in a static situation, but this is static. So the pressure at A and the pressure at B have to be equal, but the pressure at A we can think of as the pressure due to the depth of the oil. So this would be the density of the oil times gravity times the height of the column of oil. And if that's equal to the pressure at point B, well, the pressure at point B is due to the depth of the water column. So this is density of water times G times height of water. Might as well cancel out the G on both sides of the equation. And if we're trying to solve for the density of the oil, pretty simple. It's just the density of water multiplied by the height of the water divided by the height of the oil. So this is equal to 1,000 kilograms per cubic meter multiplied by, we just have to read what's given here. The height of the water is 24.5 centimeters and the height of the oil is 27.2. Those units cancel out. Grab a calculator and see what you get. 24.5 divided by 27.2 multiplied by 1,000 gives very nearly 900 kilograms per cubic meter. In other words, the oil is less dense than the water, which can be seen by virtue of the column of oil being taller than the column of water. Okay, so that's part A. Part B asks us to find the absolute pressure at point B, which is the interface between the water and the mercury. So again, we'll use the equation for gauge pressure and note that absolute pressure is equal to atmospheric pressure plus gauge pressure. So this is going to be atmospheric pressure plus rho g h, and here we'll use density of water and the height of the water column. So this is 1.01 times 10 to the 5th pascals plus 1,000 times 9.8 times 0.245 meters, 24.5 centimeters. All right, what's your calculator say about this? 0.245 times 9.8 times 1,000 gives about 2,400 pascals. So the pressure absolute at point B is equal to, well, when we add these together, we get 1.03 times 10 to the 5th pascals. Okay. Now they say an identical tube is filled with the same amount of mercury, and then you pour the water in on this side, and you pour the oil in on this side. What happens? Originally, points A and B sat at the same height. Now we're asked, what's the new position of B relative to A? Well, because it goes into a cone shape on the left side, then the oil will not go as high. It's going to be the same volume of oil that's poured in, but it won't be the same amount of height. So that means when all is said and done, if we draw this again, this cone shape that sits on top of the U-tube has to reflect a case of static equilibrium. And so if this represents the top of the oil, then the mercury will probably sit about here. And there's your point A, there's the point B, and there's the water level. So point B is now going to sit somewhat below point A to create equilibrium. And that's due to the fact that the height of the oil is no longer 27.2 centimeters. It's going to have to be something less than that if this is still the same volume of oil. Okay, and then part D, a small piece of wood is placed in the oil. What's that going to look like? If we put a piece of wood here and it floats in the oil, well, the only way it can float, the only way we can have a free body diagram that says there's some buoyant force acting upward to offset the weight of the block of wood is if the oil, right, density of oil times gravity times volume, there has to be a volume displacement for the oil for there to be a buoyant force. And so the oil level is going to have to come up a little higher. And so that's going to increase the pressure at point A, and that increases the pressure in the whole system. So not only will the oil rise a little bit on the left, but the water level will rise a little bit on the right. And in any case, the pressure at the bottom of the whole system is therefore going to increase.